This is part 2 of a lecture on section 5.1 from Math 311, a course in linear algebra at Western Illinois University. So, in the previous video, we talked about orthogonal sets and orthonormal sets of vectors and what they mean. Now we're going to talk about orthogonal matrices. Okay, and we've already talked about orthogonal vectors. What it means for two vectors to be orthogonal and what orthogonal matrices are two different things. In fact, it doesn't make any sense to talk about two matrices being orthogonal, at least not right now. Okay, so this is a new definition for orthogonal matrices. We say that a square matrix is orthogonal if its columns form an orthonormal set. Okay, now, that seems a little strange. Why wouldn't we just call them orthonormal matrices? Well, it doesn't, and I guess the sense of orthogonality has been around a lot longer than orthonormal, that term. But anyway, so we talk about the columns if the columns are orthonormal, then the corresponding matrix is orthogonal. And remember, what that means is that if a set is orthonormal, that means it's orthogonal, and that means, take any two distinct vectors, their dot product is 0, but it also, all the vectors have to have length 1. Okay. So one way of thinking about this is if Q is orthogonal, then its columns v1 through vn have to be orthonormal. Well, what this means is the dot product vi dot vj is going to be 0 if I is not j, and 1 if I equals j. But if that's the case, we'll see that this dot product is precisely the ij entry of this matrix, where we take this is the transpose of Q times Q itself. And we see so what we're saying is that the ij entry of this is determined by this. And then that means that, well, when you think about that, if the ij entries are 0 everywhere except on the diagonal, and they're 1, well, what is it? That's the identity matrix, right? Okay, so that we're saying is that and we also see that this is Q transpose and this is Q, so we're saying that Q transpose times Q is equal to IN. All right. So if Q is orthogonal, that means Q transpose times Q is IN, the identity matrix. Conversely, we can go back in each of these steps, reverse order, and we'll see that Q transpose Q, that implies this, which implies this, which implies this, which implies this, which implies this. So we've proven our first fact in the video, is that if Q is an n by n matrix, then Q is orthogonal if and only if Q transpose times Q is equal to IN. Okay, so that's one important thing. Now we'll see that this also implies that if Q is orthogonal, or if Q is a square matrix, we see that Q being orthogonal happens if and only if Q inverse is equal to Q transpose. In other words, what we're going to show is that the way we're going to do this is we're going to show that well, not only is Q, if Q is orthogonal, it's invertible, but its inverse is going to be Q transpose. And you might think we're almost done. We already know that if Q is orthogonal, we can see that this holds. And you might think, oh, okay, well, we're done. Well, we also have to show that that Q times Q transpose is also equal to the identity, because we have to show that a matrix has to commute with its inverse. All right, so we just have to do a little bit more work here, not too much. So what we're going to do is we're going to show that Q being orthogonal implies this. So if Q is orthogonal, okay, that means from fact 1 we get that Q inverse times Q is equal to the identity, right? And in particular, that means that I'm sorry, this should be Q transpose. Oops, getting ahead of myself here. And if we take the determinants we get the determinant of Q transpose times the determinant of Q is equal to the determinant of IN, which is just 1. And we can, so in particular, it's impossible that the determinant of Q can be 0. So this means that the determinant of Q is not 0. So that means that Q inverse exists. That means that from the fundamental theorem of invertible matrices, Q is invertible, so Q inverse exists. And then we just have to show that this Q inverse is equal to Q transpose, which we can do by saying that Q inverse is going to be the same thing as I times Q inverse. And then we write I as Q transpose Q. All right. This is from the fact that since Q is orthogonal. Actually, this is from fact 1. Okay. Q is orthogonal. We have this, and then we can just use the associativity and say this is Q transpose times Q inverse, and of course Q times Q inverse is the identity matrix. So this is Q transpose. Okay. So Q inverse equals Q transpose. Okay. In the other, to prove the other direction, if Q inverse equals Q transpose, I think then it's very easy. If Q inverse equals Q transpose, then Q transpose Q is Q inverse Q, which is the identity. Okay, and that implies that Q has to be orthogonal by, again, fact 1. Okay, all right. So that proves fact 2. Okay. All right, now we have the next fact, or the next theorem we have here, shows that if, once again, if we assume that Q is an n by n matrix, then the following are equivalent. That Q is, one says Q is orthogonal, 2 says the norm of Qx equals the norm of x for all x in Rn, and the dot product of Qx and Qy is equal to the dot product of x and y for all xy in Rn. All right. These aren't terribly I think what shows you, ultimately what we want to show is that we're going to show that Q, the map that sends x to Qx, is what we call an isometry. That means if x is our input, then it says x and Qx have the same size, and we're going to use part 3 to show that the distance between x and y is going to be the same as the distance between Qx and Qy. So this gets the idea of an isometry. Okay, so what way we're going to do is we're first going to show that 1 and 3 are equivalent, and then we're also going to show that 2 and 3 are equivalent. Okay, so first show why is this true. Okay, so to show 1 implies 3. So if we're going to show that if Q is orthogonal, then why does this have to hold? So if Q is orthogonal, once again, we know this means that Q transpose times Q has to be the identity from fact 1. And then then that means that Qx dot Qy. Okay, remember the dot product can be written as like a product of matrices. It's just that the matrices are rows and columns, and in fact this is the transpose Qx times Qy. And from now we're multiplying these as matrices, and we can use properties of the transpose. This is X transpose Q transpose times Qy. And then, of course, we know that because of what we just have up here, this is the identity. So this is X transpose Y, which is X dot Y. Okay. So that implies 3. Okay, to show that 3 implies 1, we just use if we're assuming that this is true for all x and y, we're just going to choose x and y to be elements from the standard basis of Rn. So in particular, if we look at, we're going to let x be ei and y be ej, and in particular, if we consider the ith column of Q dot the ith column, the jth column of Q, this is going to be Q ei dot Q ej. Okay, it's very easy to check that. Remember that to just multiply a matrix by ei on the right gives us the ith column, and then we know that this is by what we've assumed because of 3 holes, that this is because of 3. This implies that ei this is ei dot ej, and of course this is going to be 0 if I does not equal j, and 1 if I equals j. Okay, so what this shows is the columns of Q are orthonormal, and so that implies that Q is orthogonal. All right, so 1 and 3 are equivalent. To show that 3 implies 2, so we're going to assume if this is true, if 3 is true, we want to show that this statement is true. I think we can see that if we can just let this y, if we replace y with x, we get qx dot qx equals x dot x, and that in fact will reduce to this. So this case isn't too bad. So if we let x equals y in 2, or in 3, we get that the qx, the norm of, or the distance of qx squared, the length of qx squared, this is qx dot qx, which is x dot x, and again this is by 3, which we're assuming, and this is the square of the length of x, and we can take the square roots both sides, and everything is positive, lengths are positive, so we get that qx, the length of qx equals the length of x. Okay, and then finally to show 2 implies 3, so we want to show, okay, if we it seems like this is this is a more specific narrow case. 2 is another narrow case of 3, but in fact we can use 2 to show 2 implies 3 by the following. So if 2, if we assume 2 to be true, what we can do is, instead of letting, we can let x be any vector. So we're going to let x be the difference, x minus y. So so qx minus 1, the length of qx minus y is equal to the length of x minus y. Okay, and then we can square both sides. Okay, and in fact, and then we can distribute this q. Okay. All right. Now, if we remember way back in the first chapter, we show that we could actually write this x minus the square of the length of x minus y. This is actually x minus y dot x minus y. So this is going to be x dot x minus 2 x dot y plus y dot y. Okay. And then we know that this is the length of x squared, and this is the length of y squared. Okay, so this side can be written as the length of x squared minus 2x dot y plus length of y squared. Okay, and very similarly, we can basically just do the same thing. We replace x with qx and y with qy. This will be the length of qx squared minus 2 times the dot product of qx dot qy plus the length of qy squared. So this is equal. And then we assume by 2 implies that this is equal to this. Qx, since qx equals x, or I should say the length of qx is equal to the length of x, and the length of qy is equal to the length of y. These two terms cancel, and these two terms cancel. And so we get, and then we can just divide by -2, and we get that qx dot qy has to be equal to x dot y. Okay, and that proves 3. All right. So that follows. So that's a very important fact. And again, this basically boils down to what we're saying is that the math, that in particular, this is, and I think I wrote it down right here, but I'll write it again. If Q is orthogonal, that Qx minus Qy, that length is going to be equal to the length of x minus y. Okay. In other words, so the map that sends x to qx. Okay, it's a linear transformation, but it's also an isometry. Is an isometry, meaning it preserves distances. Okay. And one example of an isometry would be like a rotation. Okay. So let's say if we have these two vectors and we rotate them through a certain angle, this distance is going to be the same as this distance. Okay. And it's going to turn out, there's one of the exercises in the book says that if you're dealing with a 2x2 orthogonal matrix, the linear transformation that it represents is always going to be either a rotation around the origin or it's going to be some reflection. Okay. Ironically, this rotation does not have to be any angle. It doesn't have to be 90 degrees. Okay. So, all right. That's the irony for this lecture. Okay, then we have this last result, which says that if Q is an n by n orthogonal matrix, so we're assuming orthogonally from the beginning, we have these results. That so let's just prove these one at a time. So to prove A, we need to show that Q transpose is orthogonal, and of course if Q transposes, then the second part follows automatically because the rows of the columns of Q transpose will be the rows of Q. Okay, so the columns of QT are orthonormal, so will the rows of Q. And here we just need the fact that we're going to show that Q transpose is orthogonal. We consider the transpose of Q transpose times Q transpose. Okay, and this is going to be the identity, because Q, obviously Q transpose is Q, and then we know that because Q is orthogonal, Q transpose is Q inverse. Okay, so this is from fact 2, and then this is the identity. So Q transpose is orthogonal by F fact 1. Right. All right. We just basically took F1 and said, you know, we have the transpose of the matrix times the matrix. It's the identity, so that matrix has to be orthogonal. B follows exactly from A. Since Q inverse is equal to Q transpose. So the inverse is orthogonal. Determinants, I think that's, you might have seen, I have concluded that from what we were doing earlier. Since Q transpose Q is equal to the identity, we can take the determinant of both sides, and the multiplicity of the determinant of Q transpose times the determinant of Q is equal to the determinant of I, which is 1. Okay, and before we, and now we can use the fact that the determinant of Q transpose is equal to the determinant of Q. Okay, so we get that the determinant of Q squared is equal to 1. And you think about, okay, well, what number, when you square it, you get 1? Well, there's only 2 possibilities, right? Either the determinant of Q is either equal to 1 or negative 1. Those are the only possibilities. For part D, eigenvalue. Now we're talking about eigenvalues for the first time this lecture. If lambda is an eigenvalue of Q, then the absolute value of lambda is equal to 1. Okay, so why is that true? Well, if lambda is an eigenvalue, then we'll have an eigenvector. So if QV equals lambda V, okay, for some non-zero V, we can how do we show that lambda is going to be what the absolute value of lambda is? Well, we know that the length of V is equal to the length of QV. Okay, and we know that this follows from fact 3, and this is the length of lambda V, and then we can use the properties of the distance function, or the length function. This is just the length of lambda times the length of V. Okay. So the length of V, we can cancel both sides, and we divide by the length of V, and we get the lambda. The absolute value of lambda equals 1. Okay, now, why can't we just say lambda has to be 1 or negative 1? Well, if lambda is real, obviously those are the only possibilities. However, if we allow for complex eigenvalues, we also get something. If you had complex numbers course before, you can talk about the modulus of a complex number is like a generalization of the absolute value function, and so we can talk about the modulus of a complex number, and what this says, it's the modulus of lambda. If lambda is a complex number, the modulus has to be 1. And basically what that means is if lambda is equal to a plus bi, then a squared plus b squared has to be equal to 1. Now, what this ultimately means is that the or the complex plane, that the lambda has to be lie on the unit circle of the complex plane. Again, if you haven't had complex variables or complex analysis or a course on that, don't worry about it. You can just assume so you just interpret that if lambda is a real eigenvalue, then it has to be 1 or -1. So we'll just say that if lambda is real, lambda is 1 or -1. And then finally, E, if the product of if Q and Q1 and Q2 are orthogonal invariant matrices, then their product is also orthogonal. And that once again, we just have to show that the product of Q1, Q2, the product of the transpose of this product times the product itself is equal to the identity, and then we'll be all set. Using the properties of the transpose, this is Q transpose 1 transpose, Q2 transpose Q1 transpose, and this is Q1 Q2, and we know that this has to be the identity. So this is because Q1 is orthogonal, so we get Q2 transpose Q2, and this has to be the identity since Q2 is orthogonal. Okay, so this is since Q1 is orthogonal, and this follows because Q2 is orthogonal. And so by fact 1, again, Q1, Q2 is orthogonal. Okay. So these are orthogonal matrices, and we're going to see that these are very powerful things. And when later on in the chapter, we're going to generalize some stuff. We're going to generalize diagonalization, and we're going to see that. Then we're going to basically replace the invertible matrix P with an orthogonal matrix, and that will lead to some interesting results. So that's all for this section. See you next time.